I'd like to now demonstrate one aspect of Bernoulli's principle, and that is, as the speed of flow increases, the pressure decreases. Now, we've probably all used these little atomizers for various purposes. As I squeeze on this bulb, I'm blowing air over a tube, and that air blowing over the top of the tube is going to be at a high speed. Low pressure, the atmospheric pressure will push it down and out through the nozzle, whatever liquid is in that bottle. We can demonstrate that another way by having an open bottle here, if you will, this open container with a glass tube, and rather than squirt air over the top with a bulb by squeezing on it, I'm going to take air from this air hose and blow air over the top of the tube, and we're going to see as the air flows over the top of the tube, what this tube will see is a high velocity and therefore a low pressure. So there'll be a low pressure inside the tube, and the atmospheric pressure will push down, push the liquid up the tube, and it'll push the liquid into the airstream, and then the airstream will blow it out and break it up into small little droplets. So let's try that experiment. Sure enough, high velocity corresponds to low pressure. We lower the pressure inside the tube, the atmospheric pressure pushes it up and out into the airstream. Now, if we can do it with a narrow tube that's fairly short, maybe we can do it with a narrow tube that's fairly long. Because inside this tube, we're talking about hydrostatic pressure as the water comes up. But up at the top of the tube, where the air is blowing, we're talking about the Bernoulli effect. So I'm going to increase the velocity over the top of this tube, reducing the pressure. That'll reduce the pressure all the way down through the tube, and we're going to see the water come up through the tube. Hopefully. Might need just a little higher velocity for this one. High velocity, low pressure. Now, of course, it takes a greater pressure difference the longer the tube is. And if we were to have a tube 34 feet long at sea level, we'd just barely be able to get it up to the top of the tube if we had zero pressure at the top, which we couldn't achieve by this process. So there are limitations on applications of this particular device. Now that we've demonstrated it for a short, narrow tube and a long, narrow tube, let's try it for a tube of this geometry. Now, you may not think of this as a tube, but I'm going to put this in the water here and let the water equalize so that it's the same level inside the tube as outside. And then I'm going to blow air over the top of the tube here, and it fans out to a large cross-sectional area. But neglecting the speed of the flow of the water up the tube will assume that that's essentially a hydrostatic situation inside of this tube here. We're going to be able to see that it doesn't really matter what the cross-sectional area is as far as the pressure versus depth inside of this tube. So I'm going to blow with a speed across the top of this tube at about the same speed that I blew across this other tube here, which was approximately the same height. And you see, sure enough it works. Just takes a little longer time because we're working with a little greater volume. But the pressure difference between the top of the tube and the level of liquid in the tank, that pressure difference is due to a velocity difference. High speed across the top of the tube corresponds to low pressure, and atmospheric pressure at the bottom then pushes the water down and up the tube and out into the air column. I'll demonstrate that one more time now that you know what to watch for. High velocity, low pressure. Bernoulli's principle.